The work of Nobel Prize has transformed our understanding of the world. While approaching the Nobel Prize winners in chemistry, we not only learn their achievements, but also the spirit of honesty, tenacity, innovation, and forging ahead.
Hello everyone, welcome to today's class, Approaching Nobel Prize Winner in Chemistry. 大家好，欢迎走进今天的课堂，走进诺贝尔化学奖。Today I will introduce you Ilya Prigogine for the structure and dissipation and life. In the history of modern natural science, there are three milestones which attract worldwide attention. The first one is classical mechanics associated with the name of the scientific jet, Newton. The second one is relativity theory associated with Einstein's name, the founder of modern physics. And the third one is the quantum mechanics associated with the name of Bohr, Heisenberg, and others. For decades, scientists all over the world have been looking up to the peak of science while looking forward to the rise of another giant monument. Ilya Prigogine, a physician who views the world from the perspective of evolution. He won the Nobel Prize in Chemistry in 1977 for his contributions to the non-equilibrium thermodynamics, particularly the theory of dissipation structures. He was born in Moscow and he worked for the ULB and the University of Texas. Thermodynamics is about the heat and its transformation into another form of energy, basically involving statistical descriptions of atomic and molecular movements. In reversible thermodynamics, process goes in only one direction, usually towards to more disorder. However, during the 1960s, Prigogine developed a theory about dissipative structures, which says that long before a state of equilibrium is reached in irreversible processes, orderly and stable systems can arise from more disordered systems. This result has been applied in many areas. Prigogine is known best due to his definition of dissipative structures and their role in thermodynamic systems far from equilibriums, and discovery that won him the Nobel Prize in Chemistry. Dissipative structure theory led to pioneering research in self-organization systems, as well as philosophy inquiries into the formation of complexity on biological entities and the quest for creative and irreversible roles of time in the natural sciences. His work is seen by many as bridges between natural sciences and social sciences. One of Prigogine's most cited papers is his Order Through Fluctuations, Self-Organizations, and Social System, in which he applied his earlier internal entropy theory, while entropy variant that S of a body or a system is split in two different components. As we shown here, one, the sum of entropy exchanges that ES, the subscript E means entropy exchange at the boundary. And two, the entropy inside shows as delta IS, the subscript I meaning entropy variant inside or internal to the system. The latter type referring to inversible processes to explain social system change in terms of the order through fluctuations. In this paper, which according to some is said to mark the beginning of social thermodynamics, Prigogine is said to model a human as an atom or a group of atoms and a family as molecule, along the way giving definitions of social entropy, free energy, among others. This internal entropy model was first outlined in his study of the thermodynamics of reversible phenomena. Underlying much of Prigogine's work was his aim to explain evolution by a new version of thermodynamics of his own formulation, a mixture of non-equilibrium or convection flow thermodynamics, fluid mechanics, and Karst theory mathematics. The seeds of this drive seem to trace to French philosopher Henri Bergson and his book Creative Evolution. This publication was said to have inspired Prigogine to reconsider the fundamentation of thermodynamics work. In his Nobel lecture, he recalled, "Since my adolescence, I have read many philosophical texts. I still remember the spell creative evolution cast on me. I felt that some essential message was embedded in Bergson's remark. The more deeply we study the nature of time, the better we understand that during means invention, creation of forms, continuously elaboration of absolutely new." In his article Thermodynamics of Evolution, Prigogine and associates state, to their credit, there are few evolutionists, though apparently very few, who recognize that critical nature of the problem of the second law and who are trying to solve it. In the years to follow, he attempted to explain evolution in terms of abstract concepts of these passive structures such as Banach cells, bifurcations, and fluctuates. The problem of the time in physics and chemistry is closely related to the formulation of the second law of thermodynamics. Thermodynamic equilibrium may be characterized by the minimum of the Helmholtz free energy defined usually by the following equation here. The second law confirms the existence of a function, the entropy S, which increases until it reaches its maximum at a state of thermodynamic equilibrium. It's easy to extend this formulation to systems which exchange energy and matter with the outside world. The second law assumes that the entropy production inside the system is positive or zero. There are three aspects which are always linked in dissipative structures. The function as expressed by the chemical equations, the space-time structure which result from the instabilities and the fluctuations which trigger the instabilities. An interplay between these three aspects lead to the most unexpected phenomena, including order through fluctuations. The microscopic thermodynamic distinction between reversible and irreversible processes has in this way to be transposed into the microscopic description. We have obtained what could be considered as the missing link between the microscopic reversible dynamics and microscopic irreversible thermodynamics. This scheme is shown as follows. Now we therefore have established in general the link between non-equilibrium thermodynamics and statistical mechanics, at least in the linear region. This is the extension of the result which was obtained long time ago in the frame of Boltzmann's theory, valid for dilute gases. Prigogine was also connected with the broader philosophical issues raised by his work. In the 19th century, the discovery of the second law of thermodynamics, with its prediction of the relentless movement of the universe towards a state of maximum entropy, generate a more pessimistic attitude about nature and science. Prigogine felt that his discovery of self-organization systems constituted a more optimistic interpretation of the consequences of the thermodynamics. In addition, his work led to a new view of the role of time in the physical sciences. Let's hear what did Prigogine say during his Nobel Prize lecture. The inclusion of thermodynamic reversibility through a non-unitary transformation theory leads to a deep alteration of structure of dynamics. But already now, the development of the theory permits us to distinguish various levels of time. I believe that this diversification of the concept of the time permits a better integration of theoretical physics and chemistry with disciplines dealing with other aspects of nature. I think Prigogine is not only a great physical chemist, also a philosopher. How do you think of him? Thank you for watching.
大家好，1977年，当被科学界誉为现代热力学的奠基人，比利时布鲁塞尔学派著名的统计物理学家普里高金，以其创立的耗散结构理论，把当年的诺贝尔化学奖桂冠举过头顶的时候，这一伟大的时刻终于到来了。人们清楚地知道，普里高金所创立的耗散结构理论，对于整个自然以至社会科学产生了划时代的重大影响，远远超出了一次诺贝尔奖的价值。普里高金于1969年在国际理论物理与生物学会议上发表了《结构、耗散和生命》一文，提出了耗散结构理论，把理论热力学的研究推向了当代的最高峰，从而在存在和演化的两种科学之间，在两种文化之间构架了一座科学的桥梁。其工作作风是：第一，普里高金是一位利用演化论而非原子论的观点来看待世界的物理学家。第二，普里高金的学术生涯是由简入繁，早年研究化学反应，中年研究热力学和统计物理，晚年深入到量子混沌的理论基础。第三，普里高金凭借自己的学识、热情与组织才能，以战略家的眼光一手缔造了布鲁塞尔学派，使得非主流的前沿研究得以长期坚持。好了，本次课到此结束，谢谢大家，再见。